Hi, welcome to Computer Science Explained. In this video, we will talk about floating point binary fractions. Floating point binary fractions are good for representing extremely large numbers or extremely small numbers. As you know from the previous video, in the fixed point notation, the position of a point, which segregates integer and fractional parts, does not depend on stored value. But in the floating point notation, position of a point depends on stored value. That is why this notation is called floating. Let's first consider standard scientific notation in base 10. For example, we have this large number. As we can see, it has a lot of zeros in the end. Let's make a more concise variant of this number. We can put a point at the very end of this number. If we shift the point one position to the left, it is equivalent to division by 10. If we simultaneously shift the point one position to the left and multiply by 10, the value will not change, because division will be compensated by multiplication. Let's repeat the procedure until the point will be after the first digit. This part is called mantissa. Mantissa is multiplied by base to the power of exponent. As we use in this example base 10 number system, of course our base equals 10. Exponent equals positive 9, because we move point 9 positions to the left. Let's consider another example. Here we move point 11 positions to the left. So exponent equals positive 11. Now let's consider this small number. If we shift the point one position to the right, it is equivalent to multiplication by 10. If we simultaneously shift the point one position to the right and divide by 10, the value will not change, because multiplication will be compensated by division. Let's repeat the procedure until the point will be after the first non-zero digit. The exponent equals negative 8, because we shift the point 8 positions to the right. Let's consider another example. Here we move the point 13 positions to the right, so exponent equals negative 13. In the floating point binary notation, all bits are divided into two groups: mantissa bits and exponent bits. Let's consider an example of 2's complement notation with 8 bits in total, 5 for mantissa and 3 for exponent. The extreme left bit of the number, or MSB, is a sign bit of the mantissa. The third bit from the right, or the extreme left bit of the exponent, is the sign bit of the exponent. If MSB equals 0, a number is positive. If MSB equals 1, a number is negative. if the sign bit of exponent equals 0, an exponent is positive. So the absolute value of a represented number is large. If the sign bit of the exponent equals 1, an exponent is negative. So the absolute value of a represented number is small. Let's consider an example with a positive number and positive exponent. Please pay attention to the weights of mantissa and exponent. The exponent equals 0 times negative 4 plus 1 times 2 plus 1 times 1 and equals 3. The mantissa equals 0 times negative 1 plus 1 times 1 over 2 plus 0 times 1 over 4 plus 1 times 1 over 8 plus 0 times 1 over 16 and equals 5 over 8 or 0.625. Now we need to multiply mantissa and base to the power of exponent. As we have the base 2 number system here, of course the base equals 2. So 5 over 8 times 8 equals 5. Multiplication of mantissa by base to the power of exponent is equivalent to shifting floating point in mantissa by exponent positions. If an exponent is positive, to the right, and if an exponent is negative, to the left. In this example, we can see that when we shift the point, the weights of mantissa are changed. Here we shift the point 3 positions to the right, because the exponent is equal to positive 3. Let's check the number. 0 times negative 8 plus 1 times 4 plus 0 times 2 plus 1 times 1 equals 5. So two different methods give us the same result. Now let's consider an example with a negative number and positive exponent. The exponent equals 0 times negative 4 plus 1 times 2 plus 0 times 1 and equals positive 2. The mantissa equals 1 times negative 1 plus 0 times 1 over 2 plus 1 times 1 over 4 plus 1 times 1 over 8 plus 0 times 1 over 16 and equals negative 5 over 8. The number equals mantissa times 2 to the power of exponent. So negative 5 over 8 times 2 to the power of 2 equals negative 5 over 2 or negative 2.5. Now let's consider an example with a positive number and negative exponent. The exponent equals 1 times negative 4 plus 1 times 2 plus 0 times 1 and equals negative 2. The mantissa equals 0 times negative 1 plus 1 times 1 over 2 plus 1 times 1 over 4 plus 0 times 1 over 8 plus 0 times 1 over 16 and equals 3 over 4 or 0.75. The number equals mantissa times 2 to the power of exponent. So 3 over 4 times 2 to the power of negative 2 equals 3 over 16 or 0.1875. Now let's consider an example with a negative number and a negative exponent. The exponent equals 1 times negative 4 plus 0 times 2 plus 1 times 1 and equals negative 3. The mantissa equals 1 times negative 1 plus 1 times 1 over 2 plus 0 times 1 over 4 plus 1 times 1 over 8 plus 0 times 1 over 16 and equals negative 3 over 8 or negative 0.375. the number equals mantissa times 2 to the power of exponent. So negative 3 over 8 times 2 to the power of negative 3 equals negative 3 over 64, or negative 0.046875. Thanks for watching. See you next time.